So here we have question 1 of the 2021 Scholarship Chemistry exam. The first thing we need to do when we analyze a subproblem is we need to break it down into what we're actually being asked. So first thing is to read through it. So we're initially told that we have this piece of calcium metal that's dropped into a beaker containing this amount of distilled water, and we get this colorless gas produced and a solution without any precipitate. Then, upon adding extra calcium metal to the same beaker, we not only get the colorless gas again, but we also get a precipitate forming in solution. And when we add dilute hydrochloric solution again, this becomes clear. Okay, so first thing to note then is we need to justify these observations. And what that means then is we need to explain it in these different steps that occur. Firstly, being the initial piece of calcium metal that's dropped in. Secondly, when the precipitate forms, and thirdly, when when the precipitate disappears again. With these types of questions, first thing to do is to write out some balanced equations. So what we have here is the dissociation of calcium hydroxide, and we can write the balanced equation here. Keep in mind this is a solid and it's going to be dissociating into Ca2 plus ions and hydroxide ions. And keep in mind that this is 2OH minus just because it's balanced. And then, so that's our dissociation equation. But we also have another equation to set up, and that's going to be our reaction of calcium with water itself. So we get the solid, and we add water, and we know we have to get calcium hydroxide here. But to balance this equation then, and we're not really sure what this colorless gas is, we can also note that in calcium hydroxide we get two oxygens, and the only source of oxygen here is water, so this has to become 2H2O, leaving us with H2 gas left. And aqueous. Okay, so these are our two equations that we've set up. Next is to do the quantitative parts with this calculation. So what we can see here is we're given this mass of calcium and we're given the volume of water. What that then means is we can find the concentration of the calcium in solution. So first thing to do is find the moles initially in calcium. We can use this using the formula mass over molar mass. So that's small m over big M. And so the mass here is 0.185. And the molar mass of calcium, which you can find in the periodic table, which will be provided in the resource booklet, is 40.1. That then leaves us with 4.6135 times 10 to the power of negative 3 moles of Ca. Now, this is in 750 mils of solution. So concentration of calcium hydroxide, and also just note that moles of Ca equals moles of calcium hydroxide, just because of the fact this is a 1-to-1 ratio. So that means then that the moles of calcium hydroxide is also 4.6135 times 10 to the power of negative 3 moles. And calculating concentration, we can rearrange the formula N equals CV. So we get C equals moles over volume, or this, and the volume here. Now, just keep in mind it's given in milliliters, so this needs to be converted to standard units. So that's going to be in chemistry dm cubed or liters. So in this case, it's times 10 to the power of negative 3, so 0.75. That gives us a value of 6.151 times 10 to the power of negative 3 moles per liter. Okay, so what we can then do is we can also then just find the concentration of OH minus, and that can be done just because of the fact, again, from this equation here, you see this is a 1 to 2 ratio. So therefore, concentration of Ca2 plus is just going to be the concentration of calcium hydroxide. Again, just look at the first balance equation, this one here. So we have the concentration of calcium ions, and we have but we can calculate the concentration of hydroxide ions just by multiplying it by 2. So it means that concentration of OH minus equals 1.23 times 10 to the power of negative 2 moles per liter. Okay, now what we can do is we can go back and we can use the value given to us of calcium hydroxide being 6.4 times 10 to the power of negative 6. Now, what this value means is that in a fully saturated solution, when we have the value of the concentration of calcium ions times the concentration of OH minus ions squared is going to equal that. We can show this here using this equation here. Then this is just derived from your normal equilibria. So that's what we get here. That's the maximum that can occur. Now, if we can calculate what the expression here is by multiplying 6.151 times 10 to the power of negative 3. And this is going to be the reaction quotient. So we can call this Q times 1.23 times 10 to the power of negative 2 squared. And that's going to give us a value of 9.31 times 10 to the power of negative 7. Now, 9.31 times 10 to the power of negative 7 is going to be less than 6.4 times 10 to the power of negative 6. So therefore, we don't actually get any precipitate formed since it hasn't reached a fully saturated solution. And once a solution and this volume of water can't take on any more of the calcium hydroxide ions, then we're going to start seeing the calcium hydroxide precipitating outwards. So we can just say, therefore, there's going to be no precipitate formed. Okay, moving on then, what we can then do next is try and find the additional moles of calcium that's added. And we can then see why that's going to add a precipitate. So the moles of extra calcium that is added, so the total moles is going to be 0.396. Sorry, the total mass is going to be 0.396 of the 2 extra pieces of calcium metal. We can find moles through a similar method as before. So we have 0.396 over the molar mass. That's going to be 40.1. And that gives us a value of 9.875 times 10 to the power of negative 3 moles additionally added. Similarly then, we can calculate concentration, and we can do this through using this value of the moles of calcium hydroxide, equating it in a 1-to-1 ratio to the moles of calcium that's added, since 1 mole of calcium added equals 1 mole of calcium hydroxide. And we can calculate the concentration of calcium hydroxide additionally in solution from that. We can show this here. This is going to be over the same volume. So, and remember to convert it to liters. So this is 0.5 liters. That gives us 1.317 times 10 to the power of negative 2 moles per liter. From here then, the concentration now in solution of Ca2 plus and OH minus is just going to be this value times 2 to the original values that we had earlier. So concentration of calcium 2 plus ions in total is going to be equal to 1.317 times 10 to the power of negative 2 plus 6.151 times 10 to the power of negative 3. And this is with our initial moles of calcium. And this gives us a value of 1.932 times 10 to the power of negative 2 moles per liter. Now you might be asking why we can just add the concentration when normally you would add the moles here. And that's because of the fact that this is in the same solution. So it's going to be the same volume of water. And why you could definitely go ahead and convert everything to moles and convert it back to concentration. Everything will just cancel out. So with scholarship exams being quite time pressured, this is a good way to save some extra time. Now, concentration of OH minus in total is going to be this value here multiplied by 2 times the original. So that's going to be 2 times 1.317 times 10 to the power of negative 2 plus 1.23 times 10 to the power of negative 2, and that gives us 3.864 times 10 to the power of negative 2 moles per liter. And again, we can find the reaction quotient of this. So we calculate the value of Q again here, and remember it's Ca2 plus and OH minus. So this equals now, we just find the values again, 1.932 times 10 to the power of negative 2, and this is going to be times 3.864 times 10 to the power of negative 2, and this is squared. So don't forget to square it, which gives us approximately 2.88 times 10 to the power of negative 5. And you'll note now that Q is actually greater than the maximum solubility, because maximum solubility is only 6.4 times 10 to the power of negative 6, meaning that therefore we get a precipitate. The precipitate here is calcium hydroxide. Now, generally, with group 2 hydroxides, they're basically all going to be white precipitates. So if you struggle with inorganic chemistry and identifying colors and stuff, that's just a general rule of thumb that you can get. Okay, now, so what happens when we add in some dilute HCl? Now, when you add HCl to H2O, we get this reaction here. Well, actually, really, it shouldn't be a double-sided arrow since it goes to completion. So we get the hydronium ion, and we get Cl minus, right? Now, what this means then is we get an increase in H plus ions in solution, and you'll also note from earlier that solid calcium hydroxide dissociates into your calcium 2 plus ion and your 2 OH minus ions. So this added H plus is then going to react with your OH minus to then form water. Therefore, as we consume OH minus from this side of the solution, from Le Chatelier's principle, it then drives it further to the right to try and compensate for this added change. So therefore, as concentration of OH minus 4s, the equilibrium is going to be driven towards the right, and therefore we actually get an increase in dissolution of calcium hydroxide, meaning that the precipitate is going to be dissolved. And we can just write up our answer as saying that as OH minus, concentration of OH minus 4s, equilibrium of dissolution of calcium hydroxide is driven to the right, resulting in precipitate dissolving as OH minus is consumed. And as OH minus 4s, if we refer back to the reaction quotient equation, once Q is going to be less than the Ks, it will have completely dissolved. That's why we get this clear remaining solution with no solid.